So this is the second lesson on the vector of a plane. Just to remind you what we learned last time, we saw the three different forms of the equation of a plane. First of all, the vector equation of a plane here. Then we saw the Cartesian form, and then finally we saw the normal form of a plane. What we're going to do in this lesson is have a look at a few examples and see how we use those different forms. First question. Here we've got to find the equation in Cartesian form of a plane that contains a point and it's got the normal vector 3i minus 2j plus 4k. So that would look like this. There's my point, that's my normal to the vector to the plane, and the plane is there for us. What we've got to try and do is somehow find the equation of that plane. So what we're going to need here, we want the Cartesian form, but given that we've got a point and the normal, let's start with the normal form of a plane. So that's going to be r dot n is equal to a dot n. All of those are vectors. R is our general point, a is a specific point on the plane, and n is our normal to the plane. So we'll start off with our general point, x, y, z. The normal is 3 minus 2, 4. A is our specific point on the plane, 3, 1, 1, dot 3 minus 2, 4. So what we've got to do, that's obviously in the normal form. What we've now got to do is convert that into Cartesian form. So pause the video, do it yourself, and come back and check. There we go. So that is the Cartesian form of the equation of the plane in this case. Right, let's try another one. Okay, in this case here, what we've got is to find the equation of a plane that passes through 3 points. Then once we've done that, we've got to see if there's a fourth point that lies on that plane. We sometimes say, are they coplanar? Let's just visualize that for a second. So 3 points is what we need to define a plane, and there we have 1, 2, 3 points lying on that plane there. And what we've got to do, here's the fourth point, and actually it's almost cheating here, I can see that that's not the case, they don't lie in that plane. What we've got to do is check and show that that doesn't actually lie in the plane. So first thing is we've got to define the plane, and there's two formats we're asked for, and then to check that that lies or not on the plane. Right, in the question, first of all it asks us for the vector form of the plane. So I'll remind you, a vector form looks like this. We've got a specific point on the plane, then we've got two directions. So a multiple of one direction and then a multiple of another direction. So A is a point on the plane. We've got 1, 2, 3 points that we could choose there. B is a direction in that plane. C is another direction in that plane. So how are we going to get B and C from that? Well, one thing that we could do is find two vectors in the plane. And given that we've got 3 points, that's quite easy. The vector A to B is going to give us a vector in the plane. So we can do that by working out O to B and subtracting O to A. So O to B is the position vector of B, O to A is the position vector of A. So that gives us a vector 1, 1, minus 4. So A to B is a vector that's in the plane ABC. That's one of the directions that we could use there, for example B. Right, let's repeat that now to get a second direction in the plane. We could work out A to C or B to C, it doesn't matter. It would both give us the correct answer. So B to C is OC subtract OB. So there we go. So now we've got all the elements that we need to be able to create this. To get the equation of a plane in vector format, we need a point on the plane, so I'm going to use A. We need a direction on the plane B and a second direction on the plane C, and those are the two that I'm going to use. So let's put them all together. So the equation of the plane in vector format is going to be 0, 2, 6. So I've used A there. Now I could have used B, I could have used C, it didn't matter. And then I'll do a multiple. So my parameter lambda there of 1, 1, minus 4. And then mu lots of the other one, minus 2, minus 1, 2. And that gives us the vector equation of the plane. Now, given that we could have had chosen different values for this point here, could have put in A, B or C, or I could have even, if I really wanted to do, use the midpoint of AB, midpoint of BC. We can have multiple formats. Lots of different answers here will give us the correct equation of the plane. So that's something to look out for when you're looking at your answers. So we found the equation of the plane there in vector form. What we're going to do now is try and work it out in Cartesian form. So one way of doing that is to shift it into the parametric form and then try and eliminate the two parameters lambda and mu, but that's got a few issues. Let's just see why. So if we rewrite that, so what we're trying to do here is eliminate the parameters lambda and mu. So I could write x is equal to lambda minus 2 mu, y is equal to 2 plus lambda minus mu, and z is equal to 1 minus 4 lambda plus 2 mu. So what I'm going to try, what I would try and do here is try to eliminate mu, try to eliminate lambda, and just have an equation with x, y and z in. And quite often it's easy to go wrong with that, and my preference actually is not even to use this method at all, and to start again really and work out the normal equation of the plane and then switch into the Cartesian. So to find the normal equation of the plane, just remind you I want this form here. R dot n is equal to A dot n. So R is our general point x, y, z, and n is our normal vector. So how can I get a normal vector from the information we're given, since we're not given the normal to the plane? However, what we are given, or what we have worked out here, is two directions to the plane. So 1, 1, minus 4 is a direction in the plane, and minus 2, minus 1, 2 is a direction in the plane. If we were to work out the vector product of those two, that would give us a vector that was a normal or perpendicular to those two. So I'll invite you now to try and do that calculation yourself, and don't forget to check it with the dot product, and I'll have it back for you in a few seconds. Pause the video. Okay, so that's my vector that I've got, minus 2, 6, 1. I've checked it by doing the dot product with that vector and one of the previous directions. That gives me 0, so that shows that these two vectors are perpendicular to each other. I could really do it with the second one, or I should really do it with the second one, but I'm confident I've not made a mistake because that's given me a value of 0. So here we go. This is our normal vector to the plane, minus 2, 6, 1. So going back to our equation here, in the normal form, r dot n is equal to a dot n. So A is going to be a specific point in that plane. Let's use the point A, 0, 2, 6, although you could use any of the other three. And we'll do the dot product with that and the other one. And once we work that out, minus 2x plus 6y plus z is equal to 18, isn't it? Okay, so that is our Cartesian Cartesian form of the plane. Here's the vector, here's the Cartesian, and here, if you like, is the normal. Right, let's remind ourselves of what we're asked for in the question. So we've got the vector form, we've got the Cartesian form. What we're asked to do now is to see whether the point 1, minus 1, 4 lies in that plane. So we've created a plane that's got the points A, B and C in. Does D lie on that plane or not? Or another way of asking that is, are A, B, C and D coplanar? So in other words, what we're going to try and work out is, does the point D, 1 minus 1, 4, lie on this plane? And this is a very simple thing to do. All you've got to do here is substitute the values in for X, Y and Z for that point and check that they equal the value. Because if they equal 18, that means it lies on the plane. If they don't equal that value, it doesn't lie on the plane. So minus 2 lots of 1 plus 6 lots of minus 1 plus 4, does that give us 18? Well, I think it gives us minus 4. So as that's not 18, that means that that point does not lie in the plane. D is not in the plane A, B, C. Or if you like, A, B, C, D are not in the same plane, they are not coplanar. Right, another example. What we're looking at here is the angles between two planes. So here's a plane in Cartesian form, here's another plane in Cartesian form. What I want to do is find the angle between the two. So again, here's a visual representation of that. Those are the two planes. We can see, well actually there's two angles that I could find there. One here and another one there. So which one do I want? Well, if we go back to the question and read it, it says it wants the acute angle there. So what we're after is this angle here. Right. Now then, the clue to this is in looking at the normals. So what I can find with the equation of a plane is the normals to those planes, and I could consider that angle there. So how is that possible? Well, first of all, let's just see what we're after. This is the angle, theta. This is the angle that we could find using the normals. And actually, with a bit of geometry, you'll see that those two things are the same. Why? Well, just have a look at that for a second. We've got a straight line here, of course, or it's a flat plane. So that's 180 minus theta. This, of course, is a right angle. That's a right angle. So if you work out this angle here, it's theta. So those two angles there are the same. So I could change the question to what's the angle between the two normals to the plane. So how do we find that? Well, if you remember, this is the Cartesian form here, and we can switch from the Cartesian form back to the normal form very, very quickly. So just to remind you one more time, r dot n equals a dot n is our normal form. X, Y, Z here dot the direction of the normal is going to give us our value here. The dot product of those is going to be 6 in this case. So this vector here is going to be the normal to the plane. Well, you can see that the calculation of x, y, z dot 2, 3 minus 4 is going to give us the left hand side of this equation. And similarly, therefore, the normal to this plane is going to be minus 1, 1, minus 2. So I could ask the question, find the angle between 2, 3, minus 4 and minus 1, 1, minus 2. Now then, you should know how to do that. You're going to need the dot product. I'll ask you to pause the video and try to do that for yourselves. Okay. here we are back again. So we're trying to find the angle between the two normals. You should have found the lengths of those vectors, root 29, root 6. You should have also found the dot product of those two vectors, which is 9. Put those together to find you the cosine of the angle, and the angle gives you 47.0 degrees, which is the acute angle that we're after. And that's how you find the angle between two planes.